Hello, my name is Aniket Bose and today I am going to demonstrate the experiment about Wheatstone bridge. From the lab manual, I have summarized all the objectives. So here are the objectives. The first objective is to measure all the resistors in the Wheatstone bridge and build the Wheatstone bridge. So let's measure the resistances, but before that, let me tell you how I am going to do the experiment. So I am going to use a 1.5 kilo ohm resistance in this around these 2 points, here and here. Around these 2 points, I am going to use a 1.5 kilo ohm resistor. But because I don't have a 1.5 kilo ohm resistor, so instead what I have done is I used a potentiometer to generate a 500 ohm resistance and put that in series with a 1 kilo ohm resistance. So let's measure these resistances in the circuit. So here is the circuit and I am going to measure the first resistance, which is Z1. So the value of Z1 is 1.5 kilo ohms, as you can see. Now the value of Z2, this is Z2, it is 10 kilo ohms. Now let's check Z4, this is Z4. So let's check Z4. So the value of Z4 is 100 kilo ohms and this is Z3. As you can see, Z3 is 15 kilo ohms. Yeah. So our first objective, which was to measure the resistances, is completed, and we also built the circuit. Now let's check the second objective. The second objective says derive the expressions of potentials at each node. Now we are applying a known potential around these 2 points. So we don't need to find the expression for these 2 points. We only need to find expressions for potentials at these 2 points. So what I have done, I generalized the whole circuit. I added a fifth resistance or fifth impedance here, and as you can see, I also at this node I have applied a potential E, and at this node I have not connected this node to ground. Instead, I have applied a potential E ref. So now to find out the expressions for VA and VB, I have used nodal, and after a long calculation, I saw some repeating patterns, and I labeled them using some random letters of random alphabets of English letters. And why I did that to simplify or to reduce the length of the expressions, and at the end I got this expression for VA and this expression for VB. Here M, S, R and N, these are all known values in terms of E, E ref, Z1, Z2, Z3 and Z4. Because we already know E, E ref, Z1, Z2, Z3 and Z4, that's why M is also known. So the values of M, N, R and S are already known. Now these two expressions are for the general circuit. To find out the expression for the simpler circuit, as you can see in the lab, from the lab manual, we didn't had a fifth resistance here. So what I did is instead of calculating the nodal again, I replaced the Z5 with infinity to basically open circuit A and B. So try to find the limiting value when Z5 tends to infinity, what will be the value of V and what will be the value of VB. So the expression for the simpler circuit came out to be this M by R for VA and for VB N by S. So the second objective is also done. Now let's look at the third objective, that is to measure the node potentials experimentally to verify our expressions which we calculated from the step 2 or the objective number 2. So let's verify the expressions from the measurements. I will use the multimeter to measure the voltages. By the way, this M by N and R by S are with respect to this M by R, and N by S are with respect to ground. Now in the circuit, as we are using 2.5 volt as the reference, so we basically need to, and we are using the multimeter, one of the probe of the multimeter here as the reference. So to find out the voltages of at A with respect to the reference potential, we basically need to find out the difference between the reference potential and the VA value with respect to ground. So that's what I did, and in the I used the Desmos to calculate the value. So here are the values of resistances, and we also have calculated the values of M, N, R and S. And then here is the VA with respect to ground, which is M by R, and VB with respect to ground, N by S. Then to find out value of VA with respect to the reference in the circuit, we subtracted E ref from value of potential at A with respect to ground, and these are the two values for the balanced case. As you can see, both the values of VA and VB are same, 2.17, 2.17. So the value of VA minus VB is 0. So let's check out that in the circuit. So this is 5 volts and this is 2.5 volts. I am going to power up the circuit. The circuit is powered. Now let's measure the first potential VA with respect to this reference. So this is coming out to be 2.19 or 2.20. As you can see in the Desmos calculation, it's 2.17. So it's coming out to be close. And now let's look at VB, which should also be 2.17 because the bridge is in balanced condition. So as you can see, it's in the potential at B with respect to the reference is 2.16, close to 2.17. Now as they are same, the values of V and VB, so the actual value of VA with respect to VB will be 0, as you can see also here. Yeah, they are close to 0. Now we are going to do the experiment for unbalanced case also. From our objective, the third part is done. We have measured the node potentials experimentally and verified our expressions. Our expressions, the calculations from our expression was giving the same result as the measurement. Now we are going to do the same experiment for we are going to repeat this all of this 2 and 3 for unbalanced case also. Now because I have generalized the expression, so this is going to hold for unbalanced case also. Now to get to the unbalanced configuration, what I have done, I have replaced Z2 with Z4, Z4 with Z3, and Z3 with Z2. As you can see now, Z1 Z4, if I do this replacement, then Z1 Z4 will not be equal to Z2 Z3. So let's check that out in the circuit. Now let's measure them if they are correct or not. So Z1 should be, I didn't change Z1 from its place, so Z1 should be, Z1 is 1.5 kilo ohms as it was previously. Now this has become the Z2 has become 15 kilo ohms, so it's 15 kilo ohms. Now Z3, which is this, will be 100 kilo ohms, 100 kilo ohms, and Z4 is 10 kilo ohms. Now let's again apply the potential and let's measure all the potentials. But before going to do that, in the Desmos, I am going to change the Z1 and Z2, Z3, Z4. So I have replaced, I have changed Z2 with Z2 with Z4. So let's make it Z4, and then Z4 goes to Z3. So Z4 becomes Z3, and then Z3 goes to Z2. So this has become Z2. So now as you can see, Z1 into Z4, this Z1 into Z4, which is this. These are not same as Z2 into Z3. Now the values of VA with respect to the reference are here and VB are here. So let's check out that in the circuit. So this is 5 volts and this is 2.5 volts. Now VA with respect to the reference is 2.27. In the Desmos, we can see the VA with respect to reference is 2.27. VB should be 0.227. So let's check that out. So this is VB, it's 0.227. In the Desmos also it's 0.227. So our expressions are correct. So these expressions are working for both balanced and unbalanced case. Now the objective to measure the node potentials experimentally and verify our expressions for both balanced and unbalanced case have already been done. Now we need to find out the Thevenin equivalent of the circuit. So to find out the Thevenin equivalent, we basically need the open circuit voltage across VA and VB. So we have already done that. That is for the balanced case, but we need to find out the Thevenin equivalent of the circuit for the unbalanced case, because in the next step we are going to do some sinusoidal excitation. So let's check out that. So VA minus VB, this is coming out to be 2.03, 2.04. In the Desmos also you can see this is 2.04. The Thevenin potential with respect to the reference is 2.04, and the Z Thevenin value is 20k. Let's check that out also. Z Thevenin is a resistance when there is no power source. So I have disconnected the source. Now let's measure the resistance. As you can see, the resistance is 20 kilo ohms. In the Desmos also you can see that the Z Thevenin is 20 kilo ohms. So we verified the expressions with the measurements. We have also find out the Thevenin equivalent. Now in the fifth step and the last step, we need to connect a capacitive load across node A and node B and give some sinusoidal excitation in the Thevenin equivalent and find out the cutoff frequency. So in the circuit, what I have done, I have used this capacitance. This is 100 nanofarad, but there are some tolerances. So this is plus minus 20% tolerance, comes with 20% tolerance. So it becomes 80, and in the circuit when I plug it, it becomes much less than that. So let's check that out. In the breadboard, the value of capacitor reduces for some reason. So as you can see, this is 50.5. It will go up to 53 or 55 something. Yeah, it's around 55. So this is around 55. In the Desmos, I have replaced the value of C with 55 nanofarads. Now the VThevenin was coming out to be 20k, right? But I didn't have a 20k resistor. So what I did in the circuit, you can see here, I have used a 10k and 10k in series, and then the capacitance. I am going to now give a sinusoidal excitation. So I'm going to get the excitation from channel A of this ADLM kit. So let's put that channel A here. This is channel A. And for the reference potential, I am not going to give ground. I am going to give VThevenin, because I don't want the signal to get clipped off. So VThevenin, the value of VThevenin was, let's check. So value of VThevenin was 2.045. So what I am going to do is generate a 2.045 DC from the channel B. So let's give this to channel B. And to measure the, to get the cutoff frequency, I am going to find out the capacitor, the signal around this capacitor. So I am going to use the B in pin to measure the voltage across the capacitor. And because the capacitor filters out the higher frequencies, we will get only the lower frequencies. So let's check that out. So in the channel A, I am going to generate a sinusoidal voltage of which will vary from 0 to 2 VThevenin, which is 2.045, and I am going to give a starting frequency of 10, and this will be source voltage. Shape will be sine. Then in the channel B I am going to source a voltage of DC, and because we also need to measure the voltage around capacitor, that's why I have splitted the input and output. Now the DC will be 2.045 volts, so that I have given here. Now let's run the oscilloscope. So as you can see, when the frequency is 10 hertz, both the signals are overlapping with each other. If I increase it, so let's do it to 30. Here also they are almost same, and there is no clipping because I have used VThevenin for the ground, and for the for the maximum value of the excitation I have used VThevenin, and that is VThevenin plus or minus VThevenin sin omega t type signal. So for the 30 hertz frequency, they are overlapping mostly. Now let's make this big. So as you can see, they have like the output, the voltage across the capacitor have decreased, and this will decrease more. So the cutoff frequency, which is 144 hertz. So let's check out the potential at 144 hertz. So as you can see, at 144 hertz, the peak to peak voltage is 1.703 minus 0.310. So 1.703 minus 0.310. This comes out to be 1.393. In the cutoff frequency, you can see the voltage value is 1.44, which is near to 1.393.